So yeah, thanks, Femi. And yeah, really excited to be the first person in this seminar series. I'm really excited to looking forward to the rest of the year. Um, so yeah, my name is Matthew Carr, and I am a PhD student at the University of Cape Town from South Africa. And I'm going to be presenting some work from the first chapter of my PhD, which is investigating the influence of the Indonesian Throughflow on the Seychelles-Chagos Thermocline Ridge and the surface chlorophyll bloom. And I just like to thank some of the funding for this project was through the Bertarelli Foundation, as well as the South African Environmental Observation Network, which is SEON. So just some background. The Seychelles-Chagos Thermocline Ridge is a region of open ocean upwelling in the Southwest Indian Ocean. And so this upwelling is driven by the tropical gyre and the large-scale wind circulation in the region. And the uplift of the water column brings nutrients into the euphotic zone. And this makes the region really biologically important because it promotes the development of chlorophyll blooms. And this is quite important in the Indian Ocean because the interior of the Indian Ocean is generally oligotrophic. So this is almost like an island of biological activity. So the main aim of this project was to link the physical ocean dynamics to the biology in the region. And this project is mainly a modeling project, but in order to set a platform for our numerical model experiments, we started with observations from remote sensing and in situ observations. And so this is what I'm going to be presenting today. And this figure from Rospelli et al. In 2009 just gives you a really good idea of the size and the shape of the upwelling region. So this is temperature integrated through depth to 80 meters, and we can see the upwelling ridge. So from previous literature, we know that the Indonesian Throughflow, which is the waters coming from the Pacific Ocean through the Indonesian islands and into the Indian Ocean, has quite a strong influence on this upwelling region. So these two figures are from Agua Gonzalez et al. In 2016, and they show the absolute dynamic topography, which is a variable for sea surface height, as well as the temperature at 100 meters depth from the World Ocean Atlas. And you can see that the upwelling region is expressed at the surface through the absolute dynamic topography. So the 0.8 meter contour quite well represents the upwelling at the surface. And you'll see within this contour, we have two local minimums, which are known as the Seychelles Dome and the Chagos Dome. And you can see that in the temperature, you can see that these are the local minimums in thermocline depth, and you can see this at the surface. And the second important takeaway from these figures is that we can see the influence of the Indonesian Throughflow waters. So as the waters come through the Indonesian Straits, they enter the Indian Ocean. And you can see this highlighted by the 1 meter ADT contour. And as this water moves into the basin, we can see that the upwelling region shifts to the west and is resized. So these Indonesian Throughflow waters, they have quite a strong signal in both temperature and salinity. And so this is highlighted. So these are vertical slices through the ocean basin using the World Ocean Atlas 2018. And what's really nice about these slices is that you can see this entrance of these Indonesian Throughflow waters entering the basin in the east as warm, less saline waters. And as we go through the year, we can see how these waters spread out as a light buoyant plume across the basin. And what's really interesting here is you'll notice the 20-degree isotherm, which is generally used as the thermocline in this region. You can see as these waters spread out, you can see a deepening of the thermocline. So this shows this interaction of this Indonesian throughflow waters and the upwelling region. As these light buoyant plume spreads across the basin, you see a deepening in the thermocline, which is a suppression of the upwelling. So seeing this interaction in the physical oceanography, we started to investigate what are the links to the biology. So to do that, here we have the same seasonal climatologies, and we have the absolute dynamic topography as the black contours, which represents the physical oceanography, the size of the upwelling region. And in the colors, we have the surface chlorophyll concentrations. And this is from a merged ocean color product. And we can see the strong coupling between the physical, the size of the upwelling region, and the biological, which is the chlorophyll concentration. And we can see, the strong coupling between the two. And we can also see very clearly in winter, we have a strong bloom season. So you can see a strong increase in the amount of chlorophyll at the surface during the austral winter. And so in this figure, I've also marked these two green stars, which are the position of two moorings, which are part of the Rama marine array that we're going to use a bit later in the analysis. So seeing the strong coupling between the biology and the physics, we want to investigate not just the seasonal timescales, but also interannual variability. So in order to do so, we had to define some areas to do some time series analysis. So here we've defined the two areas aimed at the Seychelles Dome and the Chagos Dome, which you'll remember are the two local minimums. So the Seychelles Dome is the blue box, and you can see that it's a dynamic box. So because we have this seasonal westward shift of the upwelling region, we used the lowest value of absolute dynamic topography in the 0.8 meter contour, and that's where we centered the box. So seasonally, we have a dynamic box, whereas for the Chagos Dome, which is the red box, we have a static box, and this is based on the previous literature that I mentioned at the start of the talk. So using these boxes, we then looked at the interannual variability, and especially focusing on the relationship between those Indonesian throughflow waters that are coming through the Indonesian Straits and the upwelling region. So here we have the time series. So this figure is a little bit busy when you first look at it. So I'm going to try talk it through as clearly as I can. So what we have here is we have the monthly anomalies of the surface chlorophyll for those two boxes. So for the Seychelles box, which is dynamic, and the Chagos Dome, and which is the blue line in the time series. And then we also have the monthly anomalies of a transport proxy. So this transport proxy is a proxy that we use to calculate how much Indonesian throughflow waters are coming through and entering into the Indian Ocean, sorry. So how we did that is we used the three transects that you can see on the map on the top left, and we calculated the volume transport through each of these sections and averaged and took an average. And so to calculate the volume transport, we used the derived geostrophic currents from remote sensing, and we just assumed that these geostrophic currents from the altimetry are constant from the surface to a depth of 10 meters. So integrating from the surface to a depth of 10 meters and across this section, we obtained a volume transport. And so this is what we used for volume proxy, like I said, to try give an indication of how much water is entering the basin. And what you can see is that you get a really nice inverse correlation at the Seychelles dome. So we have this relationship where if you have an increase in the transport proxy, so a stronger Indonesian throughflow, more Indonesian throughflow waters entering the basin, you have a decrease in surface chlorophyll, and vice versa. When you have weaker Indonesian throughflow, so less water entering the basin, you have an increase in the surface chlorophyll at the Chagos dome. And so what we saw this, and we wanted to, so because this region is very dynamic and there's a lot of factors at play, we highlighted just the extreme events. So transport, which is either in the 10th or the 90th percentile, representing very strong or very weak transport. And that's what you can see is the red highlighted areas in the time series, as well as in the scatter plots. And when you only use the extreme events, you get an even stronger relationship. So it seems that when transport is particularly strong or particularly weak, we get a better relationship with the surface chlorophyll. And what's very interesting as well is that you'll see we have this strong relationship at the Chagos dome, but this relationship is much weaker at the Seychelles dome. And this is not unexpected, because if you remember to the position of the boxes, the Chagos dome is much closer to the entrance of the Indonesian waters, to the east of the basin, where the Seychelles dome is quite far across to the west. So it's expected that these Indonesian throughflow waters are going to have a less of an impact all the way to the west of the basin. So just to highlight this in a little bit more detail, this figure we have here is a spatial correlation. So it's the same correlation using the monthly transport proxy, monthly anomalies of the transport proxy. But here we use the monthly anomalies of surface chlorophyll for each grid point that you see in the shaded figure. And you can see that we have the relationship which is much stronger in the east of the basin, and this relationship is much weaker as we move across to the west. And that's sort of intuitive. As you move further away from the Indonesian Straits, you have less of an impact of these Indonesian throughflow waters. So we saw this nice relationship in the transport. And like I mentioned, the Indonesian throughflow waters have quite a strong salinity signal. So we started to look if we could see the same relationship in using salinity. So for this time series, we use those same two boxes, but here we have the average surface chlorophyll, the monthly anomalies, and we have the monthly anomalies of surface salinity from remote sensing. And again, you can see that we have this very strong relationship at the Chagos dome, where you have increased salinity, you generally have higher surface chlorophyll, and you don't have the same relationship across the basin at the Seychelles dome. And this positive correlation makes sense if you think that the Indonesian throughflow has generally a lower salinity signal. So if you have a strong Indonesian throughflow event, you're going to have a lower surface salinity and lower surface chlorophyll, and vice versa for weaker Indonesian throughflow events. So looking at this relationship, we wanted to identify a few case studies so that we can investigate the mechanisms of why we're having this relationship, and as well as giving a spatial context to these case studies. So we identified again, so the extreme events, so using the transport proxy, where we had transport events in the 10th or 90th percentile. And if these events occurred during the surface bloom season, that's how we identified our case studies. And I'm just going to show two. This first one is a case where we have a weaker Indonesian throughflow. And in this case, you can see that we have 0.8 meter contour representing the upwelling, much further to the west than the climatology. And it reaches over the box that we used for the Chagos dome. And this is associated with relatively high surface chlorophyll values. And this last bottom figure is really nice. This is the data from the Rama marine array that I mentioned earlier. So this is just the more eastern Rama marine that's in the box that we defined as the Chagos dome. And you can see that the thermocline is relatively stable at about 70 meters. And sorry, the shading is salinity. So we have relatively stable salinity through the water column. And if we compare that to a case study where we have a stronger Indonesian throughflow, so more Indonesian throughflows, waters entering the basin, you can see there's quite a strong difference in the absolute dynamic topography, where you can see the 0.8 meter contour is further to the west, and we have this big signal of Indonesian throughflow waters, which is the 1 meter contour, reaching both the Chagos dome box as well as the position of the Rama marine array. This is associated with slightly less surface chlorophyll. And what's really cool is that you can see in the Rama marine array, we have this big decrease in the depth of the thermocline. So that's the thick 20-degree isotherm. And this big decrease in the thermocline happens at the same time as we have this fresh warm water reaching the marine array. So this speaks to the mechanism of potentially why we've seen this relationship between the surface chlorophyll concentrations and the transport proxy, is that it seems like if more Indonesian throughflow waters enter the basin, as they enter, it seems to push down the thermocline. And this is through buoyancy fluxes. If you remember that this water is less saline, warmer, so it sits on top. And this suppression of the thermocline, or pushing down the deepening of the thermocline, is suppressing the upwelling and then potentially leading to less nutrients entering the euphotic zone and less opportunity for a surface chlorophyll bloom. And so if we look at the Rama marine arrays for the full time period, so this is the two Rama marine arrays with the green star representing the the Chagos dome in the east, and the red star, the Seychelles dome in the west. We can see again here we have salinity as the colors and the black contour as temperature. We can see these regular intrusions of low salinity waters that are relatively warm at the Chagos dome. And every time we have these intrusions, we have this big deepening of the thermocline. And whereas if you look in the far west of the basin, we have from the Rama marine array, we see that this relationship doesn't really happen at the Seychelles dome. And that speaks really nicely to the previous relationship that we saw. So it appears that this Indonesian throughflow water enters the basin and has interannual variability, which pushes down the thermocline, resulting in a resizing of the upwelling area and the surface chlorophyll bloom in turn. So the limitations of this work, as I said, this work is mainly being done by observations, and this area is very dynamic, and it's strongly influenced by large-scale climate modes such as the Indian Ocean dipole, ENSO, things like Rossby waves. And these things are quite hard to pick apart and untangle through the observations because everything is acting together at once. And the work is mostly limited to the surface because we mostly used remote sensing observations. Apart from the Raman marine arrays, we don't really know what's going on at depth. So things like the deep chlorophyll maximum, we don't have any information about that. And so to overcome this, we're going to start to develop numerical models. And the idea is to run some simulations where we can change the inputs of these Indonesian throughflow waters and investigate how that impacts the upwelling and as well as the biology, because we aim to couple these numerical models with a biogeochemical model. So I hope that was clear enough and it wasn't too fast. And if anyone's got any questions, I'm happy to discuss. And thank you again for the opportunity to present.
Great, thank you very much, Matthew, for this very interesting talk. I will now open the floor for questions. So if anyone has a question, please raise your hand or just write it in the chat box. So maybe I will start with a question which is in the chat box. By Sudesh, do you have any nutrient measurements from this region or their ratios?
No, so that's a good question. I feel the in situ observations, from what I know, are relatively limited, especially over longer time periods. So I think that's getting much better with the bioargos, and I think there's a few cruises in the area that are happening. So I think that's going to improve quite a lot in the next few years. But from what I know, the nutrients, the in situ observations are a bit limited in the area.
I hope that answers the question.
Yeah. So the answer is no. We don't have any nutrients observations yet.
Hi, Matt. Thank you for this interesting talk. I do have a question. Recently we heard about this Kudos program. They are taking a lot of, ship observations in this Seychelles region. So is that data available to the public? Like, can we access it? Do you have any idea about that?
Yeah, that's a very, very good point. So I think the cruise has it happened, or is it I think it was planned for quite this period, and I don't know about the data availability, but that would be a great source, like you say, of in situ observations, because they are servicing those some of the marine arrays that I mentioned in the talk. So it would be great to collaborate and to have some in situ observations. I think one of the issues, I guess, or why remote sensing is a great tool, because it's sort of a basin scale study. It's such a large study area that in situ obviously is super, super helpful, but it's always going to be quite of a smaller spatial scale and temporal scale, where we're looking at quite large spaces and temporal time scales. But it would be great to have more in situ. And like I said, I think also a lot of bioargo have been released, I think by the Kudos cruise and other cruises in the last few years. So that would be a great source of data.
Thanks, Matt, for this interesting talk. I have a question.
Sure.
You perhaps looked at the lag between, so you said there was a weak link between chlorophyll and the transport in the Western Indian Ocean. Have you perhaps looked at the lag between them? Because sometimes it takes about, a few months for the mass of water to travel all the way to the west.
Yeah, for sure. I had done some lag correlations, and so I think I forgot to add as well that transport proxy is a 3-month rolling average, so that accounts a little bit for the time delay. But I think that's a really good observation. That's something maybe you can get a higher relationship between the two with a bigger lag. That's a good observation.
So there might be other processes that are driving the chlorophyll in the
For sure. But I think also if you look at the Rama marine array, I guess you do see some of that low salinity water all the way in the Seychelles Dome region, but it's not nearly as prevalent as at the Seychelles Dome, at the Chagos Dome. So my feeling is that the water properties maybe get mixed as they move across, and it doesn't have the same effect of it loses its buoyancy as it moves across potentially. But that's a good. I should look at the lag correlation.
And there's a comment from in the chat box from Sudesh. Thank you, Matthew, for your answer of the question. I think you must try for getting some nutrient measurements from the region and try to correlate with chlorophyll variabilities. Would make more sense and interesting than correlating with physical parameters.
For sure, definitely. And I think that kudos cruise would be super helpful potentially if the data is available to get the nutrient observations.
I have a question, Matthew. So would you go and say that the transport of the Indonesian throughflow, so the water mass coming in through the Indonesian throughflow, could be a predictor of chlorophyll concentration or upwelling, or the shape of the upwelling in the Seychelles-Chagos Thermocline Ridge?
Yeah, or that would be super interesting. So that I think will come more with the modeling experiments, because if we can simulate this process well, we can start to quantify how important this factor is, because like I said, there's a lot of dynamics at play, like the wind forcing is very important for the upwelling. And you also have things like Rossby waves that impact the depth of the thermocline. So it's very hard to untangle or quantify how much influence these water masses have on the upwelling region. Like I think from the study, it looks like it definitely has a role, but using it for prediction, I think it's quite hard if we don't know how much of a role it has, if that makes sense. So I think the modeling studies will really help to pick apart, like give us some solid numbers of how big an impact these water masses have. And then, like you say, prediction to the future, because I think as the climate, as we have climate change and climate variability, the amount of waters coming through the Indonesian passages is predicted to change. So if it has a very, very strong impact on the upwelling, it's gonna these changes are going to have a strong impact in the biology of the region. So potentially through the modeling, we can start to quantify some numbers, which would be really, I think, quite helpful.
Thanks, Matthew. We have another questions in the chat box from Santosh NIO. So CIOB is a low benthic biomass area, less than 0.5 gram per square meter for macrobenthos. What do you think Indonesian Throughflow is responsible for low carbon sink to bottom sediments in the region?
Yeah, that's I'm not sure if I can answer that one, to be honest. My background is strongly physical oceanography, and I'm just starting to step into the world of the biogeochemistry. So I can't answer that, I'm sorry.
Another question in the chat box: is there a seasonal or interannual variability in the relationship between the Seychelles-Chagos and the Indonesian Throughflow?
Yeah, so that's for sure. So there's the seasonality we can see is this is quite nicely shown with this figure, where you have this resizing which happens every year, and this Indonesian Throughflow inputs on a seasonal time scale. And then there are interannual variabilities, and this is what we're trying to pick apart, is if we have interannual variability in the Indonesian Throughflow waters, how is that affecting the upwelling region? And that seems to be the case, is that if you have 1 year where you have more water entering the basin, you tend to have a smaller upwelling region, and then in turn a smaller chlorophyll bloom. So yeah, definitely there's both the seasonal and interannual relationship occurring.
Thanks, Matthew. Oh, sorry. Did you want to add something? Another question in the chat box. How could the variations in monsoon patterns we experience now affect the model and predictability?
Yeah, so that's a very good question, because obviously the monsoons are going to have a big impact on the large scale wind, which is definitely going to impact the upwelling. For the model simulations, we're going to start with climatological runs for our investigations. So we're going to use foreseens that are climatological, so that they're repeating each year. So we aren't going to use for our initial experiments any interannual variability. So changes in the monsoon probably won't be captured in the initial model runs. And then obviously if our climatological runs go smoothly, then it'll be very interesting to add interannual variability into the model runs. And then things like changes in the monsoon pattern we can potentially quantify how much that impacts the upwelling. But for now, the first few experiments will just be climatological. So we won't include changes in the monsoon yet.
Matthew, I have a
Yes.
follow-up question to this. So you talked about this Croco model in the talk. So can you touch a little bit upon it, because
Sure, yeah. So Croco it's a numerical ocean model that branched off from the ROMS configuration. And it's a community model. I think it's developed mainly in the European Union and in France. And so and our experiments, so you can either run the ocean model with interannual variability, where you have you put the inputs from the atmosphere with changes through time, and the inputs of the ocean with interannual variability. But our experiments, we're just going to have a seasonal climatology repeating, and we're going to try see if we can recreate the seasonal upwelling and the seasonal dynamics of the region. And then we are going to artificially increase the amount of Indonesian throughflow water coming through. So we'll have one model, which is a reference model, where we try represent the area as best we can using this model, and then artificially increase the amount of water coming through, and then see if that dampens the upwelling. And then, so I don't know if this is, maybe I've diverged from the question, but so the Chl-a model, it's the numerical ocean model. So it simulates the currents and the temperatures and all the physics of the ocean. And then you can couple that with the biogeochemical model, which is Piscis. And so that will represent the life cycles of the chlorophyll bloom and the nutrients. So if we link the two, we can kind of see a direct impact of our experiment, which is completely like an artificial event, and how that will impact the plankton bloom. So yeah, sorry, I hope that, did that answer the question?
Yeah, thanks.
Sure.
Yeah, I have one question. I'm from question from Chandan. Okay, I have one question. Yeah, what about the input parameter for this biogeochemical model? Whether it is like only the phytoplankton or zooplankton, or it is like size fraction phytoplankton or something like that. What?
Yeah, so that's a good question. I have experience with the Chl-a model. Coupling it with the biogeochemistry is going to be completely new for me. So that's going to be next year and the year afterwards task. So I don't think I can answer that with any anything solid yet, but in 2 years' time I'll come back to that and I'll let you know. But I know the model has a lot of tuning, where a lot of the parameters are tuned through time. But I can't speak to anything specific. I'm sorry.
Okay.
Okay, do we have any more questions from the audience? If not, then thank you very much again, Matthew, for this talk, and to everyone else, thank you for joining this first Ocean Insights. And of course, you will keep on receiving emails from us about the future events. Great, thank you, everyone.